we're very happy to have Rob from Perimeter Institute, and he's going to tell us about quantum extremal islands, and he's going to make it easy. Great. Thank you, Rob.
Okay, thank you, Hugo, and thank you all for being here and the invitation. It's great to visit Berkeley again. There's the title, as Hugo said. There's some papers that carry that title, and I got to work with a really smart bunch of people here listed at the end. But I also wanted to mention that, oh, wrong spot. Sorry, I'm clicking in the wrong spot. Now, a bunch of these people are actually applying for postdocs. And so those of you in the audience who are looking for new postdocs, you might give their applications a look. They're a smart group of people. In any event, let us carry on. Here's my next slide. Anybody who's seen me give a talk in the past decade knows that this is my favorite slide of all time. Holographic entanglement entropy. It's this remarkable tool that's relating the Bekenstein-Hawking formula in the bulk to entanglement entropies in the boundary. And it's really been a fruitful forum for discussion or a dialogue between the bulk and the boundary, and that we've learned new things about quantum field theories, but at the same time, we've also learned new things about quantum gravity. And the message of today's talk is really that we're learning new things about the black hole information paradox. And so let's take a look at that very quickly. I'm sure that everybody's familiar, and so this is just a brief reminder. You know, what Hawking discovered so long ago was that, you know, I can think about my quantum state in the early part of the evolution in this Penrose diagram. There can be some excitations that collapse to form a black hole, but the black hole produces Hawking radiation, and with that, it's carrying away energy, and so the black hole decreases in size and eventually disappears in this evolution or this picture here. And we're just left with a late time slice with the Hawking radiation, and that's fine, except that Hawking's calculation indicated that that radiation looked very, well, it looked thermal or very close to thermal. And so that indicates that we've evolved from a pure state here in the far past to a mixed state in the far future. And that, of course, is in contradiction with the basic rules of quantum theory. Now, I wanted to talk about entropy. And so how do we turn this tension into a question about entropies? Well, if we wanted to talk about the entropy and the Hawking radiation, we would produce a curve, or Hawking's calculation produces a curve, something like that. Initially, there's no entropy, there's no radiation, but it's simply the entropy grows and grows and grows as we acquire more and more radiation here on the final time slice. Eventually, the black hole has disappeared. We're not producing any new radiation. And so the entropy then is just a constant after the evaporation time. On the other hand, Don Page looked at this and argued, well, indicated that for a unitary evolution of the system, then the entropy in the radiation had to be bounded by the entropy of the black hole. And so somewhere around the midpoint of the process, it must be that the entropy starts to decrease and eventually goes back to zero to reproduce a pure state at the on this late time slice. And so that's hinting or indicating that there must be hidden correlations between the radiation that was emitted at early times and the radiation that was emitted at late times, and that's producing this decrease. Of course, it's always been a mystery how to produce this curve from calculations involving more explicit gravitational calculations involving black holes. But then the exciting news was a year and a half ago, that we now can actually calculate the Page curve in a controlled manner. And it was really something that was kicked off by these first two papers by Jeff Pennington, and then this collection of folks. Well, I guess, well, okay, I was going to say they're on the West Coast, but they're not. There's Ahmed, Netta, Don, and Henry Maxfield. And they put out these papers showing us some new tricks on how to calculate here. And then there's also this paper that came out in August of that year, which also gave some new insights. And I'm actually going to, well, I should say that since then, many people have contributed, including people in the audience here. This list is very incomplete at this point in time, and so I apologize if I haven't included your name as one of the contributors to this field. What I wanted to do, though, is say that I'm going to focus on an output or a conclusion from this paper here, the August paper by these folks in Princeton. And what they came up with, or they encapsulated the result with what they called the island rule. And so it's easiest to think about these systems where the black hole is actually coupled to an auxiliary system where there's no gravity, and we'll call that the bath. And this reservoir then captures the Hawking radiation, and we can manipulate it or calculate with it as we usually do in quantum field theory. And then their island rule says that the entropy of the Hawking radiation is given by the usual entanglement entropy that we may calculate for that radiation, but it's not just in this reservoir. It may be that we have to include various space-like regions in the gravitating region or near the black hole. Those regions near the black hole also contribute a Bekenstein-Hawking entropy. But what we're doing, as in holographic entanglement entropy, is we're trying to minimize this combination of quantities, and the minimum is giving us the correct entanglement entropy of the radiation. So how would that work in a black hole evaporation? Well, at the early stages of the evaporation, the island is simply the empty set. And so the calculation, the saddle point that dominates is simply the usual calculation, or Hawking's calculation, of the entanglement entropy of the radiation. However, as time goes on, entanglement is building up between the radiation and excitations behind the horizon. And so then we may find that this formula is actually minimized by a combination of the reservoir and an island covering this region behind the horizon, and that this new saddle then is the one that gives us the downward part of the page curve. And so that's, in words anyway, what we were looking for, or that's what the formula tells us to do, and that's what reproduces the desired page curve. Now, there are a number of tricks or new ingredients that went into these calculations. One is that they are holographic calculations, and so holographic entanglement entropy really was a motivator here. But when we think of ADS, usually we had put reflecting boundary conditions at the edge of the ADS, and so the Hawking radiation may have reached there and then it just bounced in, and the black hole never evaporated. And so one of the tricks was coupling that system to a reservoir, or changing the boundary conditions so that the Hawking radiation could leak out of the gravity region or out of the ADS. And so that was one of the insights, to change those boundary conditions. Another comment is that many of the early calculations anyway depended on a simple two-dimensional framework involving JT, or Jaquet-Teitelbaum gravity. This is, I mean, a comment that'll come up later is that this is dual to some kind of quantum mechanics, a one-dimensional system, where there's also an ensemble average in play, and so that may be a question. But another key element is the idea that we're not just using extremal surfaces or surfaces where we're extremizing a geometric quantity, but what you can see here is we're combining the gravitational or the geometric term here that we find in Ryu Takenagi's formula with a quantum correction or with a usual quantum entanglement entropy of the matter fields. And so this is an extension that had been talked about as early as, well, in the early days by Faulkner, Lukowitz, and Maldacena, but really championed by Engelhardt and Wall here. And because we're combining those two, these are typically referred to not just as extremal surfaces, but quantum extremal surfaces. So that's a lot of words. I'd like to get more into, well, here's our magic formula. That's going to be holding center stage for the rest of the talk. But I'd like to get into more of the details, less words. I was going to say more equations, but actually I'm just going to draw more pictures to show you how this works in an example. However, there's going to be a bit of a bait and switch here, and that I'm not actually going to be talking about an evaporating black hole. Rather, the example I'm going to use comes from a paper by these three folks, and similar stuff was also studied by this UBC group, and it's discussing black holes or a black hole in thermal equilibrium. Again, their holographic model is this simple two-dimensional JT gravity. However, that's coupled as well to a CFT. And that is supposed to be, or conjectured to be, dual to a quantum mechanical system. And so what we want to do is we want to prepare an eternal two-dimensional black hole that's in thermal equilibrium with a reservoir or the two-dimensional CFT now in a non-gravitational region in this bath. And so, well, how do we do this? Well, what are we doing? We're preparing a Hartle-Hawking state. Well, we know that that's involves this, on the gravitational side, this Euclidean instanton, where now the horizon's been replaced by this fixed point here of a rotational symmetry on the instanton that involves the Euclidean time. So that's our Euclidean black hole. We want to also have the bath in thermal equilibrium. And so there what we have is the two-dimensional CFT, but it's actually in a non-gravitating region. And so we know then that how we describe a two-dimensional quantum field theory in thermal equilibrium is just to do a path integral on a thermal cylinder. This actually is on, the CFT is on a half line because we end the spatial direction somewhere and we couple it to our gravitating region. And the fact that the radius of or the circumference of the thermal circle in the bath and the asymptotic radius of our black hole match up here is just a reflection of the fact that I'm preparing both of these systems together in thermal equilibrium. So that's a nice Euclidean instanton or solution. Where is the state? Well, we know that what we do is we basically cut a line through the middle of that. We cut off the geometry, and then it's a Euclidean path integral preparation of the Hartle-Hawking state on that dashed line. So I can take this picture or the bottom half of it, and I can squash it out onto the plane. That's these semicircles or in the bottom part of this picture. And here's the state that we prepared. We can evolve that forward in Lorentzian time. In the non-gravitating region on either side, the evolution just takes us forward in flat space or half of flat space. In the gravitating region, when we evolve forward, we get the expected Euclidean or Lorentzian now black hole, which is actually in JT gravity. In some sense, it's a topological black hole, and that the background geometry is just ADS, but there are these horizons that play a special role or to create the black hole. The one thing I should have said, though, is that that's sort of the background. We should also understand that there's a CFT that it lives in this entire geometry, and that CFT is now in a thermofield double state across the dotted line. Here I've shown a picture with the Euclidean preparation and then the forward evolution in Lorentzian time. We can evolve the state forward and backward in Lorentzian time, and then we just throw away the Euclidean picture, and we get this Lorentzian picture of our black hole and the two half spaces that are attached at the asymptotic boundary. And this is then well, we have this special state along the dotted line. And then we're going to look at how various entropies grow as we evolve forward from that t=0 slice. Now, one might ask, well, why is there an information paradox, or why should there be a page curve? This is in thermal equilibrium. Nothing's changing. So where is the paradox? Well, if we think about the system at a microscopic level, what we realize is that these two systems, the bath and the gravitational region, are exchanging continuously quanta or excitations. So here's an example of two right movers that might be correlated in the thermal bath on either side of this state. This excitation is just going to wander off into the infinite flat space of the bath. On the other hand, this excitation is going to fall into the gravitational region and then eventually disappear between the black hole horizon. And so then what that represents is, well, that's increasing the entanglement between the bath regions and the gravitational region. Of course, you could also have excitations in the gravitational region that do a similar thing. You know, this one falls into the black hole, this one creeps out of the ADS space, and then wanders off into the bath. Again, that's a process that's going to increase the entanglement between those two different parts of the system. So what would the page curve look like? It would just look like the curve that we drew for Hawking's calculation of the evaporating black hole. Note that I'm describing here the change in entropy, and so it starts at 0 on my t=0 slice, and then as we evolve forward, it just continues to grow and grow and grow. If this if the equilibrium or those two systems are allowed to exchange radiation forever, you'd expect that in fact, in this case, there's no bound on how high this curve can go. On the other hand, if we think of the black hole as a quantum mechanical system, then it can only store a finite amount of information. And after a certain point, I can think that in some sense, the registers are all full, and I have to start recycling the quanta in this exchange. And so then there'd be a cap on the maximum amount of entropy, and after a certain point, the entropy or the entanglement between the bath and the gravitational region should just be fixed. In this paper, they carried out calculations using the island rule, and what they found was that that was indeed the case. There were two phases. In the early parts of the evolution, the dominant solution came just by doing the usual entanglement entropy calculations for these two regions in the bath. And that's what we'll call the growth phase, because the entanglement entropy is growing. On the other hand, at late times, a new island appeared here in the bulk or in the gravitational region. And when one calculated the entanglement entropy there, one found that in fact it was constant. And so here you have in the page phase, these new quantum extremal surfaces at these points A and minus A. And this region between them is what we call then, or what was dubbed a quantum extremal island. And it was argued that this bath radiation then carries information about the interior of the black hole. Another surprise at the time was I talked about entanglement between the radiation and stuff in the black hole interior, but in fact the island here stretches beyond the horizon. The quantum extremal surfaces were found to be outside of the black hole, and again, at the time that was a surprise. So those were beautiful calculations, you know, producing something that looked like the page curve. But, you know, it also was a time, or at least in the early days, it raised a lot of, as many questions perhaps as it answered. You know, how important was it that we were working in 2 dimensions? How important was this ensemble average that was behind the JT gravity? And in fact, I can remember wandering around the UC Davis conference or campus after an exciting talk or a set of exciting talks where we were asking questions like that. And I should acknowledge that that conversation actually set us down the road, or set me down the road that produced these papers that I'm talking about today. In any event, what I want to do today and the rest of the talk is really show you a model, a holographic model, where we can understand these new insights about the page curve, but we can understand them more from a more familiar framework or context, and that is just the usual behaviors that we see in holographic entanglement entropy. And so I'm going to try and build a general system that is in higher dimensions and doesn't involve JT gravity, et cetera, et cetera. But I'm going to pause here. I've been rambling on for a little bit. There have been a lot of words. This is just a review of other people's works, but I'll pause and ask if there are any questions at this point. Are there any questions, perhaps? If not, I'll just race ahead. Okay, here I race. So I'm going to, again, I want to build a holographic model, a more conventional model, but it's going to have some new ingredients. And the new ingredient is actually just sticking a brain into my ADS geometry, but then I'm going to use a lot of technology, or I'm going to rely on a lot of work done under the name Randall-Sundrum gravity. And so we go back almost 2 decades now and think about the results that these people had. I should mention that Andreas Karch, who was also involved in this early work, recently this spring put out a paper where he also discussed similar model and similar issues. Well, he focused, I'll mention, he focused on other issues. But the basic idea is that in the bulk of my ADS space, I just have the usual story. I've got Einstein gravity, and I'm coupling it to a negative cosmological constant. But now I'm going to stick a brain into that geometry, but it's not a probe brain. It is a brain that back reacts on the system, and we'll describe that back reaction in a moment. But the key new result was that, you know, an extra gravitational mode is realized or formed, and it's localized in the vicinity of the brain. And as a result, there's an effective theory of gravity that's associated with this new mode on the brain, and we can write down the effective action here for that gravity theory. And so you can see there's an effective Newton's constant that involves the original bulk Newton's constant and the ADS scale in the bulk. The first term here is a negative cosmological constant. And you can see the back reaction in this formula here. You know, I've got the bulk Newton's constant, it's coupling to the brain tension, and there's, you know, some algebra we do. Usually in Randall-Sundrum gravity, what they did is they tuned this factor to be 0, and then there would be no, I mean, my brain gravity theory would be just flat gravity. I'm going to tune it so that this is a small number, or a relatively small number, by which I mean that the effective curvature scale here is much, much bigger than the curvature scale in the bulk, or alternatively, the cosmological constant in the bulk is much, much bigger than the cosmological constant in the brain theory.
Hello.
Yeah.
Hello. Yeah. Where do you put brain? You put the brain in the UV region of the ADS?
I'll tell you in a moment. Yeah, in tuning this to be small, I'm actually pushing it out near the UV region. But
Okay.
this part of the slide, this empty part, is going to have lots of pictures
Okay.
to describe.
My question is whether you did do a G2 or not. I mean, RS, you do G2, right? The both sides look the same.
I'm going to do, yeah. I should, since I've been paused here, I should say that when I keep a negative cosmological constant here, that's often called not Randall-Sundrum, but Randall-Karch, which is why Andreas got involved. But yeah, you'll see that there's a Z2 symmetry in,
Z2, okay,
in the
great,
geometry and the way I set it up.
Mhm.
And so another, in case I don't say it, when I say that there's a CFT on the brain, I actually mean there are two copies of the CFT on the brain and they're weakly coupled, but that essentially is because there are two sides to my brain rather than doing an orbifold. In any event, the reason, or one of the nice things about doing this tuning is that the effective action here has a cosmological constant, an Einstein-Hilbert term, and then there are lots of higher curvature terms in the action as well. And if you look at the paper, we write down all the details of what this particular term is at R squared. But the key thing is that in this particular regime here, these terms are suppressed by factors of capital L squared over L effective squared. And so these terms can be ignored, and we essentially then are dealing with a theory of Einstein gravity coupled to a negative cosmological constant. A caveat here, and if you go and look at Andreas' paper, is because of subtleties of the model, which I really don't want to go into, the graviton actually acquires a tiny mass in this system. I'm just putting that out there to be honest, but I'm not going to talk about it at all. As far as I'm concerned, our theory is just, to all extent purposes, it's Einstein gravity coupled to a negative cosmological constant. But what is the geometry? What is this back reaction? How does it work? Well, we can fix the position or figure out the position of the brain in the usual way using the Israel boundary junction conditions. So I'm going to draw a lot of cartoons like this. This is a cross section, a time slice of ADS D plus 1. What I'm doing here with this metric is I'm actually foliating it with slices which themselves are ADS sub in D dimensions. I'm going to cut the geometry off along one of those slices, as shown here. Then I'm going to take another copy of that same geometry and I'm going to glue them together. And what we find is that there's a jump in the extrinsic curvature, and by relating that to, well, the Israel junction conditions say that that jump is related to the tension of the brain. And so given that, that tells us how to position or where to position the brain in this geometry. And as I said, or as I was saying to Yasamori, is that when we're tuning this to be small, what we're doing is we're pushing this surface out, the cutoff surface out, closer and closer to the virtual boundary here. And so we're creating a lot of extra ADS space around the brain.
Yeah, by the way, this makes the fact that the graviton become massive obvious, right? Because on the brain is not infinitely large, so there is no general covariance at the intersection between green lines and black lines. So,
why do you say the brain is not infinitely large? I'm happy to agree with you that it's massive so that we can move on, but the brain, this is an ADS space, and so this is a Penrose diagram again, or a cross-section of Penrose diagram. You know, from any point down here to up there is an infinite distance. However, in ADS space, if you're massless, you can get to the boundary in a finite amount of time. I think that's what you're focusing.
But if you cut off, if you put the finite cutoff in UV, then you can't do that in this setup, right? I mean, in usual G2, you can do it. Like you can move blank.
How about we talk about that afterwards?
Oh yeah, but yeah. Okay, anyway, it's not.
I mean, what I just wanted to mention here is I can also fix this position by just solving the equations of motion of this effective theory. You know, there's the cosmological constant term, and then there's the contribution the Einstein term, and then there's the curvature squared, and there's a whole infinite set. And what you'll find is that, well, this is the curvature of the brane, or the curvature scale of the brane. The leading order, it's just the same scale here, but if you include these terms, you'll see that this gives us an asymptotic expansion for the same results that we get here with the Israel junction conditions. And so that's just telling us about, or it's promoting the consistency between the description given by this effective theory here and the bulk theory here using the Israel junction conditions. And so the really nifty thing about this picture now is that we have 3 different ways to describe the physics. You know, there's this bulk description here where I've got ADS geometry, and it's coupled to a brane in the middle. The warning here is that this is a cartoon. Remember, there's a lot of extra space or extra geometry. The back reactions produced a lot of extra ADS in the vicinity of that brane. Usual ADS CFT tells us there's a boundary description of that as well. And there I've just got my boundary CFT. However, there's also a defect that's coupled to the theory, which has 1 dimension lower. And that's the place where the brane reaches out to infinity. And in the way I set it up, this is just a time slice is now some sphere, and the brane reaches infinity on the equator of that sphere. However, Randall-Sundrum gives us something new. Essentially, what it lets us do is holography of the defect, but not of the boundary theory. And it says that I can describe this system as an effective theory of gravity coupled to a CFT in this ADS region here, where the brane is. And that's coupled to the holographic or the boundary CFT on the rest of the sphere out here beyond the defect.
By the way, this defect is what I meant, just in case, yes.
Okay. So the nifty thing now is that I don't have just 2 ways, the usual holographic ways of describing the physics, but I've got this extra picture, which I'll call the brane perspective, or we call in our papers the brane perspective. And there what I have is a gravitational region. I got the CFT coupled to that gravity for free from Randall-Sundrum. And then there's a non-gravitational region, namely the usual asymptotic CFT that lives on the rest of the sphere. And so this is really the setup then that I was describing, or it's very similar to the setup we were describing before with the JT gravity coupled to a CFT, coupled to a CFT in a reservoir or in a non-gravitational region. Now what I want to do with well, actually I'll pause there. Were there any other questions about this setup? Because this is really given this, I'm just going to run through how the example of the black hole in equilibrium works, and we're going to discover islands. But it's really more or less conventional physics now that we're just using this holographic system. The only new ingredient is that I stuck a brane down in the bulk. I'll carry on then. How do we do black holes in equilibrium using this new system? Well, the first thing I'm going to do is I'm going to set aside the brane. I'm just going to think about empty ADS space. And I'll remind you that I can describe that empty ADS space in terms of a metric that looks like a black hole. Sometimes this is called a hyperbolic black hole. Sometimes this is called ADS Rindler coordinates. But what I have here is a coordinate system on empty ADS in d+1 dimensions. You can see that the GTT, there's a place where this goes to 0. And similarly, the radial component of the metric is blowing up at that place. The radial or the spatial slices, instead of being spheres, we've gone to a new conformal frame. And these are actually hyperbolic geometry in d-1 dimensions. So in the boundary, what I have is a CFT not on my sphere again. I've done a conformal transformation. And what I've got is the CFT on time, or R, across this hyperbolic geometry. But there are actually two copies of it, one on either side of the Reisner-Nordstrom, or the, not Reisner, the Einstein-Rosen bridge. And what I'm describing here is a thermofield double state of that boundary CFT on this geometry, but at a very special temperature. And the temperature is governed by the radius of curvature of this hyperbolic geometry here. And so this again is just the ADS vacuum, but I'm describing it in a way that what I have is actually the boundary CFT in a thermofield double state. Now, I wanted to make use of my brains, and so all I'm going to do with the brains is stick a brain down the middle of that geometry. I'm going to use the same coordinate system. And essentially what I'm doing now is I'm describing this thermofield double state, but instead of just having the boundary CFT, I've got the CFT coupled to my conformal defect. Again, I've got this geometry. The defect sits in the middle of the hyperbolic plane. And we'll talk more about that in a moment, but the temperature again is governed by the curvature radius, the radius of curvature of my hyperbolic space. So if we remember the setup that we had in 2 dimensions, it looked like this. I had a Lorentzian black hole. It was sort of a funny black hole in that the geometry here is really just ADS2. And then I had these non-gravitational regions as wings to that, or attached at the boundary. I've more or less produced something like that in higher dimensions. I now have, again, this a geometry. It's now the geometry of my d-dimensional brain. Locally, it looks like ADS, but I put a coordinate system on it where these horizons. And then there are the non-gravitational regions where the boundary CFT lives, and those are actually, instead of being flat space, they have this hyperbolic geometry across time. The other thing that you may have noticed in going from this picture to that picture is that these boundary regions now have these 2 little wings rather than a single wing, and that's because the defect is really sitting in the middle of my bath space. Before, in 2 dimensions, we cut the bath space off and we stuck the gravitational region to that boundary. Here we've got a connection in the middle of my hyperbolic space. So if I look at a Penrose diagram of that boundary space, what it looks like is just the usual diamond, the same as in Minkowski space, or that I might have drawn for Minkowski space. But now there's a defect that runs through, the conformal defect is this line that runs through the middle of the space. I'm foliating things in a way, though, that this geometry, that line, actually represents time across a hyperbolic space itself, but it's 1 dimension lower than the hyperbolic geometry of the entire slice. And so this defect really cuts that into 2 pieces, one on, well, either side. Remember, this was the picture of the ADS geometry. And so where does this picture appear? Well, it's really this diamond that fits in between the 2 orange horizons here. So it's the boundary diamond there, and the defect is where the brain reaches infinity, right here somewhere. We have a thermofield double, and so there's actually 2 copies of this. There's another diamond over here in the thermofield double, and again, another defect in the middle of that space as well. We want to do some entanglement entropy calculation. In fact, we want to, emulate what was happening before. So we want to calculate the entanglement entropy of the radiation or of the bath. So we'll step away from the defect by some small distance, and then our entangling region will extend from this boundary out to infinity in this direction, and from a similar boundary on the other side of the defect, and then extending out to infinity in the other direction away from the defect. Again, we're going to do We want all of the bath radiation, and so we're going to do this problem on this side, but we're also going to do it on the other side as well. And so we're going to ask, what is the entanglement entropy of the those 4 combined regions, one on either side of the defect in both copies of the CFT. We can ask, how does this system evolve in time? What's the natural time evolution look like? Well, if I keep the width of that little interval fixed, then in the Penrose diagram, the evolution looks like this. You know, time flows again, like in the usual Penrose diagram of flat space. And so everything's heading up to this point at the tip of the Penrose diagram. Let's look and see what that looks like when I take a cross section, say, of my ADS space here, say at t equals 0. Well, then the interesting thing is my 2 diamonds actually meet here at a point, well, which is the edge, or it's the X here on the boundary of the where the 2 horizons meet. And so before we had 4 copies of this, but the infinities all match up here at the edges of the horizon. And so I'm doing an entanglement entropy calculation where I've got 2 regions. The infinity sort of gets washed out, and I've got these 2 boundaries on this side and this side. Each of them is just a small finite distance away from the defect in the asymptotic boundary on either side of my thermofield double. If I evolve in time, then following this picture in the boundary, what I see is those, wrong way again. I see those dots moving closer and closer towards this point here, which is where the brain reaches the ADS boundary. Now, when I start drawing a picture like this, and I start talking about entanglement entropy, this may be reminiscent of scenarios that we're used to thinking about in holographic entanglement entropy. In particular, again, let's just think about empty ADS space, throw away the brain. We're used to thinking about you know, entanglement entropy questions where I have 2 disconnected regions like this, and there are always 2 different saddles, one which we'll call the disconnected, where there are 2 separate RT surfaces, each connected to, well, both either interval or either region. And then there's a connected saddle where the 2 RT surfaces actually connect the boundaries in the 2 different regions. So they extend across the ADS space. And depending on the size of these regions, we may, this saddle may dominate the disconnected phase, or the connected phase may dominate. Now, I've also shaded in the entanglement wedge, or the interior of our RT surfaces, because of the remarkable fact, one of the things that holographic entanglement entropy taught us about is entanglement wedge reconstruction. And so in this phase, there's no surprise. I can use boundary data to reconstruct what's going on in these regions very close to the boundary on either side. The surprise is that in this phase, I can use boundary data in the 2 regions combined to tell me what's going on in the middle of the space here deep in the interior. Now, that's all familiar holographic entanglement entropy. All I'm going to do is take that same picture and draw a line down the middle. That's my brain. Remember, I've actually deformed the geometry. There's a lot of extra ADS space in here. So the precise details about when I make the transition isn't going to be the same as in the other story, but they're really still just 2 separate phases. And in one case, the 2 surfaces stay away from the brain. In the other case, the 2 surfaces cross the brain. This is the phase that dominates at early times. In this case, the RT surfaces extend across the black hole or connect points on opposite sides of the thermofield double, and the entanglement entropy grows as time goes on. And the entanglement wedge reconstruction just lets me reconstruct these two regions here. This is, of course, the growth phase. On the other hand, at late time, the RT surface, we go to the connected phase here. It turns out that if you follow the time evolution using the time in that conformal frame that I chose, in fact, the entanglement entropy is fixed in this phase. But now, because we cross the brane, the entanglement wedge reconstruction allows us to use the boundary data here to learn about, in principle, what's going on in the brane. But that's precisely then the quantum extremal island from the brane perspective, where I'm doing gravitational physics in this region here. I've discovered a quantum extremal island. And so this is the Page curve where the entropy is capped off. Now, an interesting thing to do is actually think about what's going on here, not in terms of these blue regions, but in terms of the black regions. In fact, the RT surfaces are identical to what we had before, but the interpretation is one that actually was given to us by Maldacena and Hartmann for almost the same system, some time ago. And in their description, this growth of the entanglement entropy in this phase was just the system thermalizing. Eventually, the system just reaches some thermal equilibrium. The entanglement entropy surfaces, well, we use the words that they snap back. And then in these two phases, the entanglement entropy, the systems thermalize, these two black regions have thermalized. There's no more entropy growth. And so we didn't say page time or anything like that, but what we saw was that the entanglement entropy of the two black regions was constant after a while. There's also an explanation of why these red lines here are, I mean, this picture doesn't do justice, but the red lines here cross the brane outside of the horizon. So the boundaries of the quantum extremal island or the quantum extremal surfaces are outside of the horizon. And that can be described again in terms of the bulk picture, in terms of entanglement wedge nesting. I'm running a little bit behind, so I'll skip over that. I'll just say that, you know, we've reproduced, there was these pictures, this curve that I talked about in 2 dimensions. And if you go through, you can do lots of detailed calculations and you can reproduce that in any number of dimensions. And so here are some pictures from our paper with 3, 4, and 5 dimensional models that show the same or develop the same Page curve.
Rob, can I check one thing?
No, sorry, go ahead.
One slide before.
One slide before. One slide before.
Yes, so the brain should, so in your setup, your brain is like close to the ADS boundary, right?
My brain is in the middle of the space. It's this green line here, but it extends out to the ADS boundary here, where we interpret it as a conformal defect.
Right. So I mean, if you draw the full picture more in detail, then it's like the green boundary is like close to the ADS boundary.
Oh yeah, I mean, there's a lot of ADS geometry in the middle of the space here that's not represented in this cartoon.
So the right cartoon is more like there's some bulb in the middle. Is that correct?
Yeah, okay, I'll risk going all the way back. If I wanted to draw another cartoon that was more characteristic of the true geometry, it would be a picture like this.
Mm-hmm.
Instead of a straight green line, I'd have these curves, and I'd represent all this extra geometry here with that region.
So it's like the Python branch in the higher dimensions as well.
I'm not. Oh yeah, I think you're right.
More precise pictures.
Yeah, I think it is.
And showing the
yes.
Following the stories, showing the exponential complexity of recovering information. What Jeff's talking about.
I'll comment on complexity,
Oh, yeah.
but yeah.
It's not that if you use only one side. No? If you use everything, then you can.
Yes, yes.
Yes.
If I use one side,
Then it's exponentially complex. But if you use everything, it's not necessarily the case in Python.
why don't we save that for a discussion at the end? I actually, yeah, I remember that point as well. You're right. Yeah. There were lots of questions before. In our model, they all have simple answers. The question that I'm going to focus on was that in this fall paper by these three folks this was a paper that originally looked at the black holes in equilibrium. They made a very strong point about this distinguishing between a full quantum description and a semi-classical description. In particular, you might have noticed that there's an entanglement entropy of some radiation here or some bath degrees of freedom, and somehow there's a similar formula here of an entanglement entropy involving those degrees of freedom. But they wanted to distinguish what was being calculated here from what was being calculated here. And so my question is, what's up with that? Well, it's really the status of these three pictures here. One of them is not in the same footing as the other two. In particular, these two, that's the usual ADS-CFT correspondence. And I would describe that as the UV complete framework, or the one that gives us a full quantum description of the radiation. In particular, all of my real calculations were done in this picture here with Ryu-Takeyanagi formulas. And I would say that what I'm calculating then is this quantity on the right-hand side. On the other hand, there was a brain perspective, and that, just a moment, that gave me this picture of a gravitational region supporting a CFT coupled to a non-gravitational region. But I know that that is on a different footing. That is an effective theory. And for example, one of the things that Randall and Sundrum warned us of is that in this picture, it's not a true CFT, but rather there's a cutoff in that description. And so if I look at very short wavelength excitations, this isn't going to give me an accurate description of the physics. And so I want to, well, for this effective theory, that's where we're interpreting the island formula or giving an interpretation to the island formula. And so that's what I would call the semi-classical description of, well, the system. And Raphael had a question at that point.
Yeah, on your previous, I guess it's referring to the previous slide. Just in ordinary ADS-CFT, you know, I don't know, your favorite setup, ADS5×5 or whatever, dual to super Young-Mills theory. Yeah. Would you have said there that both sides of the correspondence are a UV complete framework?
Sure.
But we don't have a bulk description that's UV complete.
Yeah, but what you're saying is that I don't know how to describe this properly. I only have an effective way to describe this, but ADS-CFT says that something here is equal to something here. You're right in saying that Einstein gravity coupled to a negative cosmological constant isn't a complete description here. I mean, I have to think in terms of whatever type 2B string theory on ADS5×S5 in your example.
Right.
But I would say that that's a, if you're hung up on the word UV, I'll just say this is a complete framework.
But it's not.
What I want to stress is that this description here is on a different footing than this description here.
Yeah, that's what I'm disagreeing with.
Okay. Can we disagree at the end? Because I have like 8 more minutes and there's 20 more slides I want to run through.
Oh boy.
For Hugo. So let's disagree at the end.
For Hugo. All right.
For Hugo. Okay. So one of the things I did is I gave you, I didn't talk about it too much, but I said that I was realizing this island formula here But on the other hand, what I was really doing was I was calculating RT, ordinary holographic entanglement entropy. There's an extra term here, but just ignore that for now. I actually threw that away. We're going to set that to 0. I'm just calculating areas in the bulk, and I'm saying somehow that's equivalent to this formula. Remember, that's what we called the bulk perspective. This is what we called the brane perspective. And so they're different descriptions of the physics, but how do we connect them? And why am I asking this question? Well, it enlightens maybe some of the past discussion, but I really see it's going to be a warm-up for talking about holographic complexity and getting some interesting answers there. So let's think about the RT calculation. At a pragmatic level, when we're actually doing the calculations, we do that in 2 steps. First thing we do is we extremize the RT surfaces in the bulk here away from the brane. That's just a local equation that I can satisfy. But in fact, what it does is it gives me a whole bunch of solutions, and they all intersect the branes at different points. And so, what's fixed is the boundaries of these 2 regions in the asymptotic, on the asymptotic boundary or in the asymptotic CFT. But that data isn't enough in this particular case to fix that surface completely. And so as a second step, what we have to do is figure out, well, what is the actual surface that gives us the minimum? And I'll answer that in a moment. I'll say that I can interpret, though, these surfaces. I can look at them and I can see that, well, there's a bunch of UV divergent terms coming from when the surfaces approach infinity. That's the usual, area law term. And then there are terms involving curvature, if I'm in high enough dimensions, or terms involving curvatures integrated over the entangling surface. There are also, wrong way again. There are finite contributions coming from the area deep in the bulk here. And then there's some interesting contributions coming from where the surfaces cross the brane. Remember, these are we got pushed out towards a putative boundary. So they're in what looks like an asymptotic ADS, but there's a finite cutoff. And so they take a form that's very much like these, but that cutoff means that they're actually finite. I'm never going to take that cutoff to 0. And in fact, they can be interpreted in terms of the gravitational theory on the brane here. And so in fact, the first contribution is the area of the profile on the brane divided by the effect of Newton's constant. And then there are various higher curvature terms or terms involving curvatures integrated over the entangling surface or over this profile. And in fact, you can interpret that. You can check that this is just the Wald-Dong entropy of that particular surface given the effective action of the gravity on the brane. And so, well, another comment is that, when I go between these different surfaces here, this UV stuff near the asymptotic boundary is always the same. I always get the same answer there. Nothing's changing at that end. It's only the entropy, well, the infrared piece and this geometric piece over here that are changing when I go between these different surfaces. Ultimately, what I want to do is I want to minimize the area. And so what I'm going to do as a second step is I'm going to vary over the profile here on the brane. And I'm going to find which one of these surfaces actually gives me the minimum total area. But that we can really interpret then, or we can start to give an interpretation to it. I guess I did that in the wrong order. These finite and UV divergent terms you can associate with the quantum field theory entropy of the degrees of freedom in this region and on the brane or in the island. And well, this had a gravitational interpretation in terms of the gravity theory on the brane. And so what we got was something that looked very much, or has an interpretation as given in the island rule. And so in the first step where I'm extremizing the surfaces away from the brain, what I'm really doing is I'm evaluating for different islands this formula here. And then when I'm extremizing over the profile on the brain, I'm really varying the boundary of the island. And so I'm carrying out this extremization process. What I then want to do is I want to minimize, in my problem, I want to decide, was it the island phase or the connected phase that wins or minimizes, or is it the disconnected phase where there is no island that minimizes it? And so there's really a one-to-one match between the calculation here and the calculation here. The one distinction is that what we found is not just the Bekenstein-Hawking entropy here, but we found that we got really the Wald-Dong entropy, or the gravitational entropy of that effective theory of gravity on the brain. So a natural question that Hugo must be asking now is, well, what about holographic complexity? So in holographic complexity, we might think about complexity equals volume, where again, we'll ignore this term here, and we would just evaluate some volumes of extremal surfaces in the bulk. You know, in the brain perspective, what am I really producing? What's down here? Well, we can just apply the same analysis, the same kind of ideas, the perspective that holographic entanglement entropy gave us to try and understand what we get here. The one caveat is that I should say, I mean, I've got these subs for subregion here, so we're not looking at the holographic or the complexity of the entire state, but just these portions of the boundary. In any event, we draw more or less the same picture. We go through more or less the same steps. We extremize the bulk surfaces away from the brain. Now they're codimension 1 surfaces. That's again a local equation. And what it's doing is, well, it's hard to draw, or you need one extra dimension to draw, but there are lots of candidate surfaces with different profiles here on the brain. I should say that I've assumed that we've done the entanglement entropy calculation, and so this surface here, this RT surface, and this profile on the brain are going to be fixed, and all we're doing is extremizing or varying this surface that fills in between those two RT surfaces and the time slices on the asymptotic boundary. And just to assure you that there's a degree of freedom, or there's lots of possible surfaces, you know, if we didn't have the brain here, we'd have the other asymptotic boundary, and the full complexity problem would have been determined by fixing not just the time slice here, but a corresponding time slice on this asymptotic boundary. We don't have that boundary, and so the freedom of choosing a different time slice there is really represented by this well, the possibility that there are lots of profiles here that I'm calling B tilde on the island that extend between these two surfaces, even when I extremize in the bulk away from the brain. Again, we go through and interpret the different contributions. There's a UV divergent contribution, there's a finite IR contribution, and then there's a bunch of geometric contributions that are, again, finite and can be interpreted in terms of the effective theory on the gravity theory on the brain. What are those? Can we maybe, you know, interpret them in terms of our gravity action in the same way that we have a gravity action? We grind out some formulas and out pops the Wald-Dong entropy. Can we do the same thing here? And this is just a reminder of how you get from an action or a Lagrangian to a Wald-Dong entropy. In fact, you can do the same thing here. And this was suggested already in a paper by these folks. And there are various contributions. There's what we call a generalized volume that looks more or less, or has a form similar to the Wald part of the formula. And then there's a something we didn't give a name, that it has a K because it's like the extrinsic curvature correction here that Dong had. So there's some formula that relates the geometric terms that we found to the effect of gravitational action. And so we call this a generalized complexity equals volume for the brane theory. Again, we were stuck with many profiles. So again, the idea is let's extremize. The last step will be to extremize by varying the profile on the brane or the island profile. And so then the interpretation is very similar. From a bulk perspective, we had this simple geometric formula. Extremizing the bulk away from the brane gave us some generalized formula here that involved a geometric contribution on the brane and something that we would interpret as a quantum field theory contribution. The last step, or the second step, was I vary the profile of the island, and that corresponds to the usual maximization, that you would have gotten in complexity equals volume. Here, the surface is bounded by the quantum extremal surfaces on the brane. One thing that we make a point of doing in our paper is saying, well, okay, we've gotten this interesting calculation that gave us a generalization to higher curvature theories of complexity equals volume. Our proposal is that, well, if I'm just thinking about ordinary ADS CFT, this is the formula I should use if I'm thinking about some generalized theory of gravity theory in the bulk. You might also have quantum field theory corrections to that. There are lots of questions you could ask, but I've run out of time. I apologize. I'll just quit here and say that, this is a very interesting direction to study, and there's still lots to explore. And so thank you for your attention. I'll call it quits here, unless you want to ask questions.
Oh, let's thank Rob first. Thank you very much, Rob. And then I think we can also ask some questions. I do have some questions, but I might ask first if people want to talk about things.
Well, Raphael wants to disagree with me. I forget exactly about what, but.
It's hard, Rob. I had to wait for like an hour before I could find anything to disagree with.
Well, yeah, no, everybody should just remember that Raphael's wrong and I was right.
Okay, this is a level of
no, come on. It's late for me. I'm a little.
This is like American politics. Yeah, no, I want to just say that I guess I don't think that the doubly holographic scenario, while I think it's really interesting and really powerful in many ways, is somehow resolves this tension between, what I guess Ahmed and friends call the boldface and the non-boldface state, or the semi-classical exactly computed state. I mean, I think it remains even, and this is described in detail in a paper that Liz Wildenhain, who's I think in the audience as well, and I wrote around the same time as you guys. This is not just still there in the doubly holographic scenario, but there's sort of a specific dual to it at that second level of holography, in that you can normally when you compute the entanglement entropy of a Randall-Sundrum brane world, which you can do using Ryutake Yanagi, you would have to specify the region on the brane that you're computing the entropy of. Or if you have both a brane and a bath, you would be specifying, for example, two regions, one on each, and you could then use those classical RT surfaces to compute their entropy. But of course, that's not how it's computed in that paper. You just specify the region in the bath, and then you have a different homology rule where you allow the RT surfaces to end on the brane, and in that case. So I think these are both valid computations, and one of them is the one appropriate for that semi-classical state, and the other one is the one appropriate for that exact state. But I don't really think that there's a way to make sense of both of these states together unless you invoke something like an ensemble.
Yeah, I disagree with that. I know we're not going to resolve it tonight, or this afternoon for you, but I want to emphasize that here I stuck a brain in there, but I just use rules of ordinary ADS-CFT, holographic entanglement entropy. I didn't make anything up. I didn't make any choices. I just followed the regular rules. And the rules that are actually derived without invoking any kind of ensemble averages or anything like that. So I would, I think that's really interesting, but I just don't see ensemble averaging as being a part of the story here.
Ensemble averaging is not a part of the story that is invoked in deriving any of these rules, but it is a fact, right, that we can, for example, compute the entropy of a Randall-Sundrum brain world region using RT, and that when we do that, we begin by specifying that region and then imposing a homology constraint that has that region, as part of the boundary of the entanglement wedge. Do you agree with that?
That's interesting, actually. No, I disagree with that. Again, what I did is I used the rules.
I thought you wrote some papers establishing that. Like,
I know I did, but I'm still disagreeing with myself. Then I don't care. One of the things I'm always growing. I'm always learning.
Yeah, no, that's good.
Yeah.
No, but again, I'm going to emphasize that I did standard ADS-CFT. I followed the rules there, and what they, as I described. As I tried to describe, although it was very quick, I went from here. And what I did on the next few slides is I stared at that, and it led me to this formula here. And so I agree that you're saying there's another calculation I could have done, and there's another interpretation I could be given, But again, I'm saying this formula here, where I'm extremizing over the islands, or I'm varying those surfaces, that was just plain ordinary ADS-CFT. That's, if I did not have that, then I would not be doing this.
Yes. Can I chip in? I think I
just want to hear Raphael. Do you agree with that, or maybe you feel it's not relevant?
I would say that the island rule is just a special case of the Ryutake-Yanagi prescription. It's not a new rule.
Yeah, I guess that's what I just said, yes.
Yeah, so I agree with that. What I would just say is that there is a homology rule that we use when we compute the RT surface for BCFTs, right? Well, it's most commonly useful then. It could actually be important for any boundary theory. But the homology rule says that your RT surface is allowed to end on end of the world branes, of which which RS branes are a special case. And that's one homology rule which we can apply. And that's the one where we would go directly from the top level of holography to the sort of doubly holographic bulk and evaluate things that way. But when we start from the intermediate level, we have a choice, right? We can either compute we can apply RT to the union of what was the island that you would have found in this earlier step and the bath region, or we could apply it to the bath region alone. And it gives a correct answer in both cases. It gives the answer for the semi-classical entropy of the bath if you only ask about the bath region, and it gives the answer for the union, which follows the page curve if you ask about the union.
Yeah, I mean, the only thing I'm gonna interject again is I know. Actually, I don't know if I can find that slide. I mean, it disappeared just because I had other things to say. I mean, this was a question we got confused about when we were talking, a year ago, August. is this Planck brane really a part of the bulk or part of the boundary? Are RT surfaces really allowed to end on the Planck brane, and stuff like that? But I would have argued, again, the reason I didn't take the Z2 orbifold is because I just look at that picture and I'm not confused about the brane or the brane degrees of freedom. That's a part of the bulk theory. It's sitting there right in the middle of the bulk. How could I ever be confused to think that that's a part of the boundary?
Yep.
I mean, the reason you can be confused is because we would have said our friends, what they did is they took a Z2 orbifold, and now it looks like an edge of this diagram. But the whole reason I did not take that Z2 orbifold was so that I wouldn't be confused, or I could, well, I didn't show this slide today, but I could show this slide and to say, I'm not allowed to be confused. It's sitting there, it's in the middle of the space. But at that point, I think I'm happy to talk about it more, but
Yeah.
I know Yasamura wanted to ask a question.
Maybe
yeah.
I could just say briefly that I
Okay.
think that when you don't take the Z2 orbifold, you're preventing me from treating the brane as approximately a part of the boundary. So then I only have one thing I can calculate.
But yeah, okay, but so you would advocate that this picture, the physics of this picture, and the Z2 orbifold, those are different theories, and there's completely different physics there.
Well, yeah, I would say that's right, because there's an intermediate level that I have on the right picture, where I could forget about the fact that there's sort of a BCFT boundary level, which is just the semicircle, right? And I could go to the intermediate level of holography, which is the semicircle and the brane, but doesn't include the higher dimensional bulk. And I can ask about arbitrary subregions of that union of the semicircle and the brane.
Yeah.
I don't know how to ask such questions in the unorbifolded picture. Maybe there's a way to I mean, there should be. It's just an orbifold, but
this. My claim was that this is another effective description of the same physics here, but that you're adding an extra rule to this physics, and you're saying there's extra stuff I can do here. In fact, I can't do here or here.
Well, I'm just saying that that we do know how to compute the generalized entropy of regions on RS branes using RT and the higher dimensional bulk.
Yeah.
And the way that the setting in which I understand how to do that and make contact with the usual RT prescription is the one where I've orbifolded and the brane can be treated as an approximately regularized part of the boundary.
Yeah. Okay. But you're saying that there's something else I can do here, or there's something else I can do in the Z2 theory, Z2 orbifolded theory, that I can't do in the way that I talked about it.
Well, when I compute the entropy of the bath region in the BCFT, right, then after one step of holography, it doesn't even matter, right, if I have double holography or not. I would do the kind of thing that AEMM and Pennington did in their paper. I would look at the bulk, which is what we will later call a brane, but it's just a bulk right now, and include an island, right? Yeah. And in that description, it is just the case that in the semi-classical calculation that I use to get this bulk and the state of the bath on the brane, it looks like that part of the brane the part of the bath that I'm computing the entropy for is actually in a mixed state that doesn't follow the page curve. But then when I apply the RT prescription, it tells me it should be in a pure state. And that doesn't change. All of that is still true because I didn't have to ever say anything about whether there's a second level of holography there. Yeah. And I think at the second level, I could just start now with this bath brane system, and I could ask, in the semi-classical Hawking-like state, and I could ask, what does the RT proposal tell me about the entropy of just the bath region? It'll tell me Hawking's answer. Yeah. If I apply the RT prescription to the bath region plus the island, it'll tell me the unitary answer.
Okay.
Yeah, I mean, this is something I wanted It's absolutely no confusion. I don't know why there is any confusion.
Okay.
If you start from some most fundamental description, like no gravity, like just a PCFT, then of course you can compute the entanglement entropy of some subregion of the boundary. Then you can, that's a well-defined meaning. Okay? You can have just to calculate. And how to calculate it, and the way to calculate it is to really consider this boundary region, like the defect, as a gravitational brane. Okay? You can go to the next level and by going there, you view these microstates, correction of the microstates of this boundary or defect as a black hole. Then you are implicitly taking ensemble. That's the same as like Euclidean things is approximating state or system as a thermal ensemble. Therefore, you are really coarse graining like soft modes of the black hole. So you're like really treating ensemble black hole already by going to that picture. That's it. But the fundamentally is just a completely just unique state. And then you have a bunch of microstate associated with the defect. And those things you just chunk together and describe as Euclidean thermal state. So you're implicitly thinking about coarse graining and ensemble states. And that's the same as like a higher dimensional black hole. If you talk about a higher dimensional black hole, you have a specific microstate. But if you consider Euclidean bulk path integral, then you are taking a correction or ensemble microstates. That's why it looks like ensemble nature is there in the sense of UBC people. But in lower dimension, of course, you don't have this surface area proportional to surface area microstates or soft modes. You don't have it. Instead, you have ensemble theories. And that's why it's a dimensional reduction must reproduce a 2D theory from high dimensional theory. So it's just reproducing it that way.
I might be just getting caught up on the words, but I think you said two different things. Like when Raphael's speaking, my understanding is that you're talking about an ensemble of theories. Whereas when you're speaking, yes, and you're talking about an ensemble of states.
Yeah, ensemble of states. Yes, I would say ensemble of states. But
right, but they're different ensembles then, right?
Yes, I'm claiming ensemble of states. Yeah, I'm not necessarily agreeing with ensemble of theories.
Were you talking about an ensemble of theories, Raphael, or did I completely misunderstand?
I mean, it's a side issue. I think the important point, the point that is important to me is that in the calculations that we know how to do, which successfully reproduce the page curve, it's very important that we have an intermediate step where we do a semi-classical analysis, and that at that step, we ascribe a Hawking-like entropy curve to the bath or to the radiation or whatever plays the role of the radiation. Because if we didn't, there would be no reason to include the island. The island would not actually reduce the generalized entropy of the entanglement wedge. And so that creates a tension. One way to resolve that tension, and I have absolutely no idea if that is a general way or just that's how it happens to be in JT gravity, is to say everything that is computed in the bulk computes an ensemble average. And so the ensemble average of the entropy is 0 at the end, and the ensemble average of the state, well, with a suitable ensemble, might be a thermal state. That's all. But I don't know if this is a universal resolution of this tension. It's one resolution that may apply in some cases.
Okay.
And I'm saying that the reason why ensemble shows up in higher dimension is because you have area match of the soft modes attached, right, or microstates, like one degrees of freedom per Planck area. Therefore, these microstates provide an ensemble if you do the bulk Euclidean necessarily. But in 1+1 dimensional bulk, and horizon is a point, so you don't have that degrees of freedom. But instead, to describe black hole, like Euclidean black hole in the bulk, you have ensemble theories. You need to, otherwise you don't have this ensemble states. So the same physics or like a thermal or black hole in the bulk is reproduced differently in lower dimension because of that. That's
okay.
Maybe we should have some other people ask some questions.
Yeah.
Sure.
So if nobody has a question, I have a question. So Rob,
Okay.
when you started talking about the volume that you find sort of like a generalized volume,
Yeah.
so could I also think that that's sort of like a generalized entropy version of complexity? And did you guys find any interesting properties about this quantity? Like, is there, for instance, is it UV finite? I assume not from everything that you showed, right? Or is there some sort of monotonicity that might come from like time evolution or something? Or is this sort of like still open? Even in the case that you don't have the brain, let's imagine you just have like a two-sided black hole in higher curvature theory or something like that.
Oh, yeah, no, where's our formula here? I mean, I'm not, well, I didn't track all those questions. We didn't, like in the entropy formula, there are two different steps here.
Mhm.
And the last step is, well, you might have different candidate surfaces and you choose the minimum one. In the examples, we did a very rudimentary calculation. And so we don't know, if there's there might be situations where there's more than one candidate surface and you would choose the one that in this case maximizes.
Mhm.
But we didn't find any such example. You asked about the finiteness and no, these things diverge
Mhm.
out here, and so there are well, this quantity that you're calculating would again have some kind of UV divergences in the same way that
Yeah.
you see in the ordinary volume. I forget what else you asked.
I asked about time dependence. Like, did you see any interesting properties with time dependence?
Yeah,
like,
no, no, that would be something that's an open question. We didn't look at time dependence.
Yeah, because generally, I mean, this was more for the action than the volume, right? But generally, there was always sort of like an interesting entropy relation with the time dependence or something like that. So I was
Yeah,
just
I see what
wondering
you're
whether
saying. Yeah,
in the
no,
volume,
that's something we didn't. I mean, we really only explored this to the extent of finding this formula
Mhm.
and testing it in various ways, but we haven't yet played around with it
Mhm. To see this more like, no.
like what you're talking about.
Cool,
Yeah.
cool. Thanks.
Oh, look at that! There's Shan Ming. No, my students don't get to talk to me here in Perimeter, so they come listen to my talks.
They have to track where you're going. Yeah, so
Sorry.
any additional questions to Rob? I think I have another very simple question.
Okay.
Like, I think there was a point I haven't figured out, but that Masamichi pointed that I thought was interesting about that maybe this looking like close to the brain, sort of like the Python's launch, that like
Yeah.
and Lenny and friends. Is there anything? So like, I understand that I think their exponential complexity comes from sort of like a more outside perspective, right? It's essentially because it's hard to decode some of these gates. But it seems that the volume in the end, we are still only getting information from if there's a tensor network sort of description of the size of the tensor network, right? So I assume that in your formula, it's probably similar, right? That you're not going to get a lot of complexity from this holographic formula because of this sort of like bold region of the Python.
No, in fact, you are in some sense.
Okay.
I mean, remember what I said, where have I said? There's this UV divergence that's associated with the asymptotic boundary.
Yes.
And so this is really, this sort of brain is getting pushed out towards some virtual boundary. We've cut it off. And so this surface here isn't that far away. Or in some sense, it's like having a UV cutoff surface.
Mm-hmm.
But that cutoff is now a fixed contribution. That cutoff never gets taken to zero. It's fixed by the dynamics to be at a certain place. And so you are getting large contributions here. It's just that I'm interpreting it now in terms of these geometric quantities that are related to the brain gravity. So these are the analog of these divergences. So they are in some sense large but finite. So maybe you would say this is the Python's lunch, or this is the lunch here.
But there's still sort of like polynomial, right? In like if you think that there's a degree of freedom that like a D entropy, right, or something like that. It's still
in this formula, yeah, they are they're finite in the brain.
Sorry, did you in that formula? Did you use both sides? If you use both sides, of course, it's easy. Okay, if you use only single side, then it's exponential. This Python's phenomenon said if you use the degrees of freedom only acting on a single side of this bulge, okay? So you have like a tail and head.
Yes.
If you use only head side to represent some operator in the middle, and then you have exponential complexity. And then an easy one way to see one way to see that is like even this brain is kind of extremum surface, so you can't go by renormalization group. But even in an intense network, you can see that because of the
when I'm talking here about the complexity equals volume, I mean we started with this picture here, but just to add all the whatever to dress it up, I threw away this part of the picture, but it's, all the same stuff is happening. We're using this side as well.
Rob?
So in some sense, it's probably polynomial. Sorry, yeah?
Yeah, I'm sure you said this, but can you clarify again? In the non-orbifolded case, does the brain radiate like equally to both sides of the boundary?
Yes.
I see. So you said.
So you mean does this side pick up as much as that side?
Yeah. Like how do you actually? How is the coupling arranged?
Arranged
so from the viewpoint where I don't include the higher dimensional bulk at all. So now I have sort of a full circle, right, with a straight line being the brain running through the middle, and I'm imagining that the brain is sort of radiating stuff and it's going out into that.
Right.
Into that part of the boundary. Are we just splitting it evenly somehow?
Well, what it is there's actually, so the short answer, if you want to go home, is yes, we split it evenly.
I'm already home, so it's okay.
The longer answer is that, this is this is a caveat that I brushed over, but when I say that there's a theory of gravity on the brain and a CFT, it's actually that there are two copies of the CFT. In some sense, there's a copy associated with this region and a copy associated with this region. And they're weakly coupled because of the, they're not completely decoupled, but they're weakly coupled because of the cutoff or the fact that we've pushed it so far into the UV. Essentially, these degrees of freedom are then radiating over here, but then this is another copy of the same thing radiating over here.
You can, in fact, change like a CFT1 and a CFT2 with a defect, as long as some consistency conditions are met.
Oh,
and your setup is
I think what you're saying is you could change, say, the Newton's constant in that gravitational theory or the ADS scale.
What I meant it's a completely holographic picture, and you have a hemisphere and hemisphere. You can use the different CFTs, and you match on the equator. That's a defect. Okay? Then of course it's not radiating equally. So you kind of you can impose Z2 global symmetry, and if you just divide out by that, then it's orbifold. So it's just that. So you just impose global symmetry. You actually have a system, but it's a Lagrangian is completely symmetric.
But I mean,
think a way
but you
of
have to
representing that in the ADS is you could change, say, the ADS scale over here, and then still.
I think it's the couplings, the way the brain couples to the two sides of the boundary. So if you make that symmetric, then no one side of the boundary is ever going to have enough information to have an island. I mean, no one side is going to, right? But you could have easily chosen a coupling where everything gets moved to the right, all the radiation gets moved to the right side, in which case
definitely.
the left side is sort of superfluous, right?
Yes.
Yeah, I guess so.
And you would then have to use the old BCFT prescription for computing the RT surface, and allow it to end on the brain to get the right answer.
Yeah, I think you're right.
So if nobody has additional comments, I think Rob probably wants to to go home.
Yeah, thanks for doing
Thank
this
you.
so late your time. We appreciate it.
Thank you very much, Rob. Yeah.
Well, thank you
Write
for all the
later.
questions. You woke me up. I wouldn't have.
That's great.
Great to see you.
Very
Anyway,
good.
All right.
bye.
See you.
Okay, thanks again
Bye-bye.
for the invite. Take
Take care.
care.
Bye.
Bye.
Bye-bye.